this video. All right, so if you want to watch it again, so this video will be posted and you'll be able to see it again. I'll put it in the content library. All right, so on this one, do you remember that students worked in random groups and you were talking about what you knew about astronomy? All right, and so you guys came up with a lot of things, kind of proving that when we walk around the room and we write in independent groups, we come up with things a lot better than we do when we're sitting and just talking to people. Yeah, these were of far greater abundance and a far greater quality just in doing that from previous years. So it was interesting that you were really dredging up what you knew. All right, and one of the things that there is a general interest in is a black hole. So after the test we have on Monday, there will be a video on the black hole. All right, then August 11th through 15th, we were looking at the Big Bang Theory. So the key to this entire unit is the Big Bang Theory. So what does it explain? What does Figure 1 reveal to us, and what is a summary of the timeline that includes the formation of the structures? So this was our introduction to critical reading, if you recall. All right. Now let me try once again to take over your screen. All right. See if it was just a time thing. Oh, it keeps doing that. All right, I don't. My computer's developed a little glitch in that with Google. All right, so I'm doing the thing that has the least requires the least memory. So let's see if it any better? Or did you get another broadcast error? It's working? Okay, that's a good sign. All right. So in this critical reading, we were really doing the things that are important. So drawing. So we annotated, we looked over the crucial things, we circled or put squares around important terms, and then I always draw. There's hardly, even though I'm not great at drawing, that's not one of my skills, I draw all the time, and so do most chemists and physicists. So it's important to realize that it isn't the quality of your drawing, it's that when you draw, it helps your mind to think about something. And spatially thinking is different than just thinking in terms of words. All right, so I want to go down here. So remember we looked at this diagram and you were trying to figure out in sentences what it was that this diagram meant. All right, so as the universe expands, the universe gets cooler was one. This one I crossed out particles are expanding because it's not that are expanding, but the space between the particles that's expanding. We're right on the edge of our RAM. Yeah. And let's see what else you said. As time decreases, the temperature increases. So that would be going this way on the diagram. Normally, we read from left to right, correct? So this was a bit odd because we're talking about time decreasing going this way when we actually read going this way. All right, we read from left to right. So normally things are expressed in the way that we read. So we would say as time increases, the temperature decreased. All right. Another one that you said, as time increased, the universe became more diverse. And the word diverse is used a lot, but what is the meaning in this case? More diverse? You could say more kinds of structures, right? More kinds of objects in space, all right? And that would be like stars, all right? It would be like planets, all right, etc. But even atoms, because there were only quarks at the beginning. All right, so we had tons and tons of notes that we did on here. And here's that balloon test we did. All right, and then, all right, we added all sorts of things here. All right, so we analyzed that at about 1 second. Things have cooled down enough so normal elements like hydrogen can exist in some form. It's only the hydrogen nucleus, however. It's just a proton. This is all that can form at this point, is the nucleus. It's too hot for the electrons to stay because when it's hot, the particles are moving very fast. It's too hot for electrons because electrons are moving too fast. Let me get a smaller drawing. All right. Electrons moving too fast. Yeah, they're too fast to stay there. So the atoms can't, the nuclear charge in it, the positive charge in the nucleus can't capture electrons going as fast as they are. All right. Let me see if I can try this. Oh. All right. So over here we had questions that you were answering. So the key when we got down here is, what all does the Big Bang Theory explain about the universe? All right, so we tried to do this in groups, but I think that we didn't end up doing it in groups. I think we ran out of time. All right, so when it says what all, and this has to be really good. All right, so what all does the Big Bang Theory explain about the universe? And how many things are there? All right. The second one is, what does figure 1 reveal to us? And then the third one is, write a great summary of the timeline of the Big Bang, including formation of the structures. So that's going to involve time. This is simply going to ask about the explanation. All right, so we would write something like, the universe began in an expansion of a tiny dense, I'll just call it blob, called the singularity. All right, it doesn't need the time now because we saw that the third question is going to ask an answer about time. All right, the universe began in an expansion of a tiny dense blob called a singularity. The temperature was unbelievably hot. So I'm just writing the facts as I remember at 10 to the 32nd power degrees, which is far beyond That is unbelievable. It's hard for us to even imagine, even possibly conceive of what this is. All right. Then, as the universe expanded, it also cooled. It also cooled. All right, does that make sense? Do you see how I'm doing a little progression in my mind? All right. It also cooled. So it explained how the universe began. It explained that it started from a tiny dense blob called a singularity. The temperature was unbelievably hot at 10 to the 32 degrees. As the universe expanded, it also cooled. So we set up the conditions for cooler matter. All right. So as cooling continued, atoms developed when electrons stuck to the nucleus. With a lower speed, over time, bigger chunks of matter stuck together. Bigger chunks of matter stuck together. All right. So what I'm demonstrating here is how to just construct a paragraph that explains it from beginning to end, but in a very simple way. All right? It uses the word expansion. It uses the term singularity, dense. It talks about temperature. It gives a range of temperature that's astronomical. We talked about cooling. All right, we talked about the fact that the speed of electrons kept them from being with any nucleus, but as cooling developed, then the electrons stuck to the nucleus because they had a lower speed, and over time, bigger chunks of matter stuck together. All right, so we can see in a progression then that we would be led to bigger chunks of matter from stars, from atoms, to conglomeration of atoms like hydrogen, which is what the sun was originally made of. All right, and then we'll see in the fall of the third unit how this actually happens, how elements actually develop in the stars beyond hydrogen. All right, so those are the kind of ideas that we were working on. All right. The third one is about the timeline, where you summarize what this diagram here. So we already answered the questions about what this diagram revealed. All right, you can be sure there will be diagrams for you to analyze on the test, because that's the kind of thing we've been doing. All right. Now, let's see what's next. The next thing we did, we had another Ed puzzle on the Big Bang. All right, and so you were writing a paragraph. So remember with this, we worked on this quite a bit. This was you working out how to write a meaningful paragraph. And this is the one that talks more about time. All right. All right, so here would be an example. Now, in the video that you'll see, these things will stay longer and you can stop the video. Like right now, I'll be moving. But in the video, when you watch it, go through it, you can, and it's not going to be an Edpuzzle, so you can stop it and start it, wherever you want to go. And you can look at these pages longer, all right? So you can see what it is we wrote if you don't have that all down in yours. All right, and then the pieces of evidence support the Big Bang. Well, we found out, I can't do that with my finger. All right, we found out, for example, that we found out that one of the big things that supported it was the distribution of elements in the universe. Show that hydrogen is dominant. Show that the hydrogen atom was dominant. Which is the easiest one to make? It's by far the most abundant. All right, now, the second one are the ones we've been studying, the redshift, right? Because that one was hard to understand. The redshift of light shows through the spectroscope now we know what things like this are, don't we? Shows through this that the emission lines are redshifted. The emission lines of elements are redshifted. So if we look at hydrogens at a star, we'll see they're redshifted, meaning that star is moving away from us, are redshifted. And back then, we didn't even know what that would mean. We weren't knowledgeable enough yet to really talk about this the way we are now, that the redshift of light shows through the spectroscope that the emission lines of elements are redshifted. That is, the lines are at a lower frequency. In sound, we would say it would go from all right, redshifting shows to a lower frequency. In sound, a lower frequency sounds like a lower pitch. All right. It's probably just as well, because wouldn't this be loud if we're hearing the sound of all this redshifting going on? Yeah, it would be a cacophony of noise. All right, the third thing, what's the next thing that comes to your mind, Caleb, for a piece of evidence? Don't tell me for what when I've been talking. Have you not been paying attention at all? I'm sorry, that's not adequate. Where you should stay exactly where we are all the time. All right, what would be a third piece of evidence, Austin, for this, do you think?
No matter where you are in the universe,
okay, so there's no center of the universe because everything's moving away from us, no matter where. In the U, as we'll call it, because no matter where we could stand matter's moving away from us in all directions. Matter is moving away from us. In all directions. All right. Another huge piece of evidence that was discovered by a radio telescope. Yes. Yes. Discovery of background microwave radiation that was the redshifted product of the Big Bang over time. I'll put BB for Big Bang over time. Yeah. So microwave, the lowest radiation is radio, lowest frequency. Microwave is next to radio, so it's very low frequency light. So microwave radiation is very low frequency. Is very low frequency light. So those are the big ones. Those are the big ones because all of them really are talking about expansion that redshift reveals. And so if this was true, there should be a background radiation left over from the Big Bang. So when this was discovered in the either the 20s or the 30s, I think, 1920s, 1930s, then this really cemented the Big Bang Theory as highly probable. All right. All right, so it wasn't an explosion as much as an expansion, all right? Now, the next one we did was about what scientific theories were. This was also another critical reading that you were getting much better at doing all of the time. A special definition of the word theory and how that word is different. So when we were finished analyzing this, we had taken an article that was this big and really made it much smaller so that everything that was in the article could be explained right here. A scientific theory is an explanation. A scientific theory is about the natural world. Scientific theory requires experimentation and testing in order to be a scientific theory. So we could put relevant, reliable evidence, right? And that's what the next paragraph about. Because the next one says, but what does this evidence have to be like? Well, it needs to be relevant. It needs to be relevant to the theory. It needs to be reasonable. That is, the experimental data must be some sort of official method of research, or if it's not, something that you can bring others around to in your field so that they believe that this method, new method you created has validity. It must support the theory. And when other people try and redo your experimental work, that they get the same results. That's what reliability is. So this is how scientific theory is different from just our theory of a crime, or our theory about why somebody didn't come to the party, or our theory about which is the best house to buy, or our theory about Which country should we travel to in our vacation? All those things. We have theories about lots of things because we're thinking beings, right? But a scientific theory differs from that. And so if you recall, we analyzed older theories like the geocentric theory of the universe, where the Earth was the center and the sun moved around. All right, then we talked about this emission theory of vision, the belief that vision is caused by rays that emanate from the eyes, something that I've said I've seen in cartoons before, and X-ray eyes are seen in science fiction. All right, we talked about the Big Bang Theory, and you guys first talked about redshifting, then microwave background radiation. All right, so we were working on this again and again. Now, one of the ways that Avid promotes learning content, and it's especially important in science, did you notice how we kind of have hit the same thing over and over, but in slightly different ways? So we're looking at evidence. Mostly, we're talking about the Big Bang Theory and the evidence, and the rest of this is about the evidence. And so we learned about the electromagnetic spectrum, because in order to understand redshifting, we had to do that. All right, so this unit is so tightly constructed, not because I made it that way necessarily, but because we have to understand what electromagnetic radiation is in order to understand the evidence. All right? So redshift is a frequency change. So any sort of a shift is a change. So if you have a change, that means there's a before and an after, correct? Don't changes have a before and an after? Yeah. All right, so a change has a before. Oh, this is really just not dark enough. All right. Has a before and an after. All right. So a redshift change, that means before it was a one frequency, and afterwards, all right, a frequency we'll call it, and afterwards, no matter what that was, it is a lower frequency. A redshift is from one frequency to a lower frequency. That's why in sound, it ends with a lower pitch. Before a frequency, all right, whatever that was, and then afterwards, what we have is a lower frequency than we had previously. All right. So as we go through and look at this, so I will ask you all sorts of questions, about these, and about in the visible light, which is the high energy end and which is the lower energy end. All right, and so when you look up here, all right, when you have a high frequency that is many waves, this is high energy. And it seemed as though many of you thought that that seemed intuitively right. That since these are so tiny and there's so many packed in a small space, that means there's so many packed over a period of time. So this is high frequency. Frequency and energy go the same direction. So high frequency means high energy. Whereas over here, we can see these wavelengths spread out. All right, this looks like low frequency because these waves aren't coming very often. So in the same period of time where we've had many, many, many wavelengths, here, from here to here, we've only had one wavelength. All right, so the red end is the low frequency. All right, as we can tell. And the high end, the gamma, this is high energy, high frequency. All right. Perhaps you can think of each wavelength as packing a punch. And so over here in this space from here to here, we can see 1, 2, 3, 4, 5, 6, 7, 8. We would have had 10 punches in the face. Yeah, so each wavelength packs a punch. Here we would have just been smacked one time. Forgive me for the violence that I'm using in this. All right. So this shows about what the size are of the wavelengths. Size of the wavelengths. And now we know that the symbol for wavelengths is a Tyrannosaurus rex. That is, it looks like a two-legged Tyrannosaurus rex. All right, it's the Greek letter lambda. And that's the wavelength. And we can see the size of the wavelength here is huge. It's 10 to the 20th power. Whereas this is a trillion wavelengths. All right. This is 100 billion. This is 10,000 wavelengths. All right. So the frequency of light is actually super high. Super high. It's uncountable. And the frequency at the highest end is, there's so much because each wavelength is about the size of an atom. Each wavelength is the size of an atom. All right. So we're talking about ridiculously small wavelengths, which is why there's such a high frequency per second. All right. And so what these numbers tell you is the size of the wavelength. Okay. We also looked at what temperature produces. You can tell on my page I've had some juxtapositions. I don't know, things are not where I thought they were. But this also talks about what produces. So the hottest places in the sun, let's go over here. The hottest places on the sun produce the highest frequency radiation. Like gamma rays. Yes, such as gamma, X-rays and gamma rays. All right, and that's what this picture above was showing us. We'll go back to that picture in just a moment. All right, so in this picture you can see, all right, that here we're at a very low frequency. It doesn't even tell us. But here we are at 1K, 1 degree Kelvin, all right? So this would be absolute zero. Yeah, which we've never reached. That's such a low temperature. But we can see that the temperature just increases to the point that the things that are creating, so this is 10 million degrees Kelvin. 10 million degrees. All right? So we're talking about temperatures on the sun that are horrendously large. 10 million degrees. So the places in the universe that produce radio waves and microwaves are very cool places. All right, outer space is very cool. So outer space is down here in the black area, outer space on average is about 1K, which is why it's not only the lack of air that would be a problem if we were out there floating in space, it would be ridiculously cold. We would freeze. Yeah, we aren't meant to be aloft at that kind of temperature. All right. So your summary was, what is radiation from space called that comes from our sun? Well, we have said we were calling this electromagnetic radiation, right? And at the time we did this, we didn't realize what Maxwell had told us, that light must be made of electromagnetic waves. All right, because they travel at the same speed as the speed of light that another investigator measured. Electromagnetic waves, electromagnetic radiation. We know this means alternating electric and magnetic fields. Alternating electric and magnetic fields that are changing all the time. So what are some high energy types of radiation? So what would be the highest radiation type of electromagnetic radiation, Lizzie? What would be the highest energy?
Gamma rays.
Gamma rays, yes. Yes, and what would be the two lowest energy types, Julian? Yeah, and who are those guys even further? Yes, that's right. All right, so then we watched another video about the background radiation, and of course you can rewatch those videos as well if you'd like to. And why did the two astronomers believe microwave radiation was evidence for the Big Bang Theory? And remember, we said, well, it was because the light that was given off in the Big Bang would have been redshifted to much, much lower frequency light. And what they found, the background radiation, was microwave, and that made sense. Now, one of the videos added another evidence for the Big Bang Theory, in that when matter started pulling itself together and we started developing solar systems, all right, so as in the development of solar systems, that indicates the emergence of the gravitational force that had not existed before, as in the development of a solar system. And we know there are many solar systems, right? We could just say of our solar system to begin with, where we know that with Copernican theory that the Earth and all the other planets are revolving around the sun of our solar system. All right. Now, I wouldn't necessarily have put this in there, but it is true that gravitational force did emerge. But I'm not sure exactly how that fits. All right, but, all right. So the redshift, the cosmic background radiation of microwave, abundance of the elements in the universe, that there's so much hydrogen, and then there's so much helium, which is the second element formed in abundance and found on the sun. All right, so pretty much then, what we have talked a great deal about is the Doppler effect. All right, so I would go over this one right here. And just make sure you understand it. We did a good job, I think, on the Doppler effect. All right, so go back and look and remember the class notes. For those of you who were absent, the class notes are in the content library. So that's where I am now. I'm showing you this. Usually in the content library, though, I don't answer these questions because that's what I want you to do. All right? And we got to the point, elements have barcodes, and that's where we started this review. All right, so we are done.